and has since then been first at Caltech and at JPL as a staff scientist. His expertise is in various things related to gravitational waves. He started out with constructing templates for LIGO, and the last many years he's been working on LISA science. One of the important projects he's worked on was the LISA data challenges, organizing the community to benchmark their LISA data analysis codes to make sure who can actually do LISA data analysis when, if space-based gravitational wave missions are actually become reality. And today he will tell us about space-based gravitational wave astronomy and some statistics. Thank you.
Yeah, it's a little sad that you have to say if a space-based gravitational wave mission used to be when gravitational wave mission. So let me start with three views of gravitational waves. This is kind of the imaginative Hollywood special effects view of gravitational waves that you see in an outreach talk. It's also a good one to use if you're in the same room as funding agency officers, because you can ask them to concentrate on the rotating images, and then you get a little hypnotized, and eventually maybe they'll approve your grant. But you know, gravitational waves are fluctuation of space-time curvature, propagating autonomously and needed by very rapidly accelerating modes. So that's one representation. Another one that actually kind of occupied my mind a little bit over the last few days is this. There's all the other way in the spectrum of abstraction and idealization. So this is a Feynman diagram for a composite object, the binary effect. In this case, emitting a single gravity. It turns out that in the last few years, people have been using the machinery of effective field theory, quantum field theory, to solve for the dynamics of a general electricity binary and for the gravitational integration. This is equivalent to the very complex post-Newtonian calculations that people have been doing for the 20 years before that. But in a way, it's easier to do things the second time around. But also, it's fun and nice to do things with Feynman diagram because you can use 50 years of experience in solving complicated momentum space diagrams, and also issues like what happens to the gravitational field at a point like at the idealized point like source. So it goes to gravity, you regularize it, then you renormalize the theory. Those things are very clear from an effective field theory standpoint. Now, it's all classical, of course. We're not talking about quantum gravity. So lots of progress there, and there's expansions, post-Newtonian expansions. There are low velocity expansions of Einstein's equations. They're going towards 4pm, which is the 8th perturbative level. Another view of gravitational wave, of course, is the prototypical in-spiral merger and ring-down waveform. So this is actually the gravitational waves you see in something like LIGO. This is a waveform, maybe it's vintage 2006, I think. This may be 2007, and so the three phases are the spiral. Well, two black holes you can see are small quantized masses. They're losing energy to gravitational waves, spawning together. And then finally there's a merger, where it's all non-linear excitation of space-time, implicated horizons merge, and finally the final black hole rings down, losing its excitation slowly. Now, a few years before that, 2005 actually, we tended to use this problem in talks, but it looked like that. Okay, so this was what hip, I think, going for the first time, and then people were saying, see how exciting it is, we can do this piece with post-Newtonian equations, we can do the final piece by perturbing the whole space-time and doing the Minkowski perturbative equation lying in the middle, and it's going to be complicated and dynamic and nonlinear. Who knows what's there? Okay, what's there is pretty well behaved, it turns out. And now the analytical insight into understanding the dynamics of the merger, at least these things are not very important, can explain it essentially as a smooth, almost smooth transition between the spiral and the final ring down. So you understand this merger directly in terms of the excitation of the ring down modes of the final merged object. So that's why it looks somewhat sedate. But it did take many years of painful work to make numberical relativity work to get to this point. And so this is a view of gravitational waves, and for somebody like me, the view is actually of gravitational waves as a vessel of information, because this was just to say that the same signal you'd see for black hole binaries of different masses, just rescaled in time, because for different masses you would see different type of detectors, ground-based for stellar size black holes, space-based for big massive black holes at the center of galaxies. But this waveform is basically a vessel of information about the physical parameters of the underlying system. So the spiral depends on the individual binary, component masses, spins and orientation, the final ring down and the merger depend on the mass spin orientation of the final black hole, and these parameters are all probes into astrophysics. And really, binary physics, astrophysics and fundamental physics is probably the main dish of gravitational wave science. At least to me, the most exciting sources are binaries, and you can do a wide range of things, from understanding the physics of compact objects, stuff in the holes, in the galaxies, in our own galaxy, whether the compact binaries can be protectors for supernovae, gamma ray bursts possibly, for galactic black holes, understanding the origin and evolution with their galaxies. You can do cosmology with them, because the fact that an spiral, that the amplitude of a signal is, of course, proportional to one, inversely proportional to how far you are, and it's proportional to the masses, but also the loss of energy, and therefore the frequency of evolution is proportional to the mass, the combination of the masses, the chirp mass of the system, lets you derive an absolutely calibrated luminosity distance to the binary system. That's very good for cosmology. It's the parameter you don't get usually when you see things optically. What you get is z direction. So if you can see a gravitational wave in spiral and a electromagnetic counterpart that gives you a galaxy post for the event, you can put a point on the top of the diagram. You can also do strong field gravity, study things like whether the holes are with black holes, equation of state of neutron stars by looking at them in spirals and with other neutron stars with black holes, test alternatives to the theory of gravities. Any one of these, has probably 200 papers on the internet. It's a very subject of investigation. Now, you see black holes with the standard ways of looking for transverse oscillations. So the transverse is increase of freedom orthogonal to the direction of propagation. The basic way is to look for oscillations in the distance between freely folding reference gas masses. The implementation of that on the grounded LIGO, this is the present. This is the detector has been running for the last 10 years at this point. It's taken more than 1 year of data at design sensitivity. And this is the future. So LISA, same thing. In space, however, you use 6 lasers, 2 pairs on each arm to detect the oscillations in the distances, which are 5 million kilometers around Mars. I'll tell you, I have a slide about what's happening with LISA, but the future is also on the ground. This is ET, the Einstein telescope. So far it's a concept. It's a concept by a team of various European institutions. This will be 10 kilometers on the side compared to 4 for LIGO. It will be a triangle, much like LISA, so you have 3 independent interferometers that you can use together to see different perspectives on the waves. It will be underground, cryogenic, and you can basically see almost as far as you can do in space. You see binaries of stellar mass that goes off to 0.3 or 4. Lots of events, of course, will be very expensive, and I think the strategy in Europe is to wait for detections with LIGO and Virgo, where sufficient enthusiasm to push forward with this. But, these are the usual talking points for gravitational waves, the 10 to the minus 21. This looks small, but gravitational waves are actually powerful. They contain a lot of energy that are emitted by these very violent events. Because if you turn this into energy, into power, at a typical gravitational wave frequency of, say, kilohertz, which is a neutron star oscillation frequency, with this, so somewhere in the galaxy, with this kind of amplitude, the power per meter square is actually something like ½ a watt. So you have the same power in gravitational waves from one of these events that the we can almost see than as you have for the moon in the moon from now. However, space-time, unfortunately, is very, very stiff, so it actually deforms very quickly, even in response to so much energy. Now, so Kip, have you told this Carlo about the big dog? Yes. You have? Okay. So, informally, okay. So you may know that last year we had the first gravitational-wave event with an official name, which is the GW10 on 9/16, so September 16, 2010. The informal name was the Big Dog because the approximate direction for the event was in the Canis Major constellation. And actually, it looked pretty good in two out of three detectors. These are the time frequency traces for excitations, and this is the upward curved chirp that you'd expect from a starring spiral. Actually, so the only thing is that this event was part of a hardware injection campaign, so a blind hardware injection campaign. So an effort by the collaboration to convince itself that it could actually detect a signal had it been in the data. So this was put in the detector by actually jiggling the test masses to the right. It was put secretly, by a small group charged with this task. And then the searches were run, the detector was actually found, and it was confirmed. An envelope was opened at an official meeting of the Live Scientific Collaboration where champagne was poured just before opening the envelope, so there was something to celebrate, if not the detection, at least the fact that and a lot of work really went into this event because the idea was you didn't know what it was, but also you wanted to exercise the entire machine and the entire sociology of the thing. So not just the searches, but also an ad hoc committee set up to confirm the detection and to root out possible interference. Hoaxes even were considered as well, things that went into it. So it really tested this thing successfully. It also found some bugs in both the software and kind of the whole scheme of it. The most interesting, there were some trivial bugs. One, for instance, was that I think effectively the way this was injected, one of the detectors was flipped around. So there was a minus sign that made it effectively into a non-physical signal. Nevertheless, it was seen with wrong parameters because of that. So that was an old bug that had been corrected already, but because of the secrecy in the ejection, people used an older version of the code. So that's not even software engineering, it's more sociology that applies to that. But the part that I like about this is actually a problem of principle, which is the LIGO detector needs calibration. Since you push on the test masses to stay on the null range effectively, the system is a response as a control grouping. So you have to find out empirically what kind of displacement corresponds to what forcing, what force. That's called calibration. It needs to be repeated to interpret the signal of the detector as a gravitational wave. And it's a difficult thing to do. Experimentalists do it in various ways, but it's an improving scheme. If you do an injection, you have per force to do it with a temporary calibration, whereas the analysis was done with a better one. So this thing couldn't match by principle. Therefore, just for that, if you took the exact signal that was injected and took it out of this, the best available calibration, it would have left quite a big residual. So in a way, you couldn't quite do it right. So even if there was a software or two, I think the main thing is that the collaboration convinces itself you could find it. So the next one will be real in 3 years. So let me move on to specifics now. So I won't go through this slide in detail because it was really written for aficionados, but I guess the main thing to this is that LISA has only a slight lifetime of LISA so far is comparable to my own lifetime. However, I think on average, missions that do fly tend to have shorter time spans than average lifetimes, so I'm still hoping I can see it through. But since 1974, the first discussion, LISA really went through several different iterations. It bounced back between the US and Europe and US in response to different opportunities in the the space program. So it was originally to be two spacecraft communicating to open space and two distance ones with telescopes. Then they put 6 like that. They realized they actually could do 3. And also you see the date, the possible date of launch kept going back and forth. So 2009, last year, 2010, was probably the deciding year for all this business. Because the US astronomy and astrophysics community every 10 years has this long process, long and involved, but very serious process in which it gets together and tries to decide what are their priorities for scientific agencies for the next 10 years. This was the Astro 2010 decadal. And so the decadal came out, it was actually very flattering and very good for LISA because it gave it high priority among our space projects, basically after only WFIRST, which was a cross between a dark energy mission and a general purpose infrared telescope. And recommending an early launch. The problem is that all these recommendations were done basically looking at budget numbers that NASA really didn't have anymore, because both of fiscal tightness in the US in general, but also because of James Webb expanding, ballooning some set budgets. So basically NASA said, okay, sure, that's your number 2 priority, but we are not sure we can even do number 1. We think we can probably do only Webb this decade. So ESA, that was a joint mission with ESA, NASA had to pull out of that joint partnership, and ESA decided to explore its own European-only mission. And so this is a graphical visualization of the ESA mission. So this was actually the ESA logo for LISA. You can, if you see a NASA logo and an ESA logo, you can distinguish them because the ESA are all rotated 45 degrees. That's the main thing that distinguishes the space progress. But also, name different, they decide new gravitational-wave observatory. Really, well, lots of imagination there. Also, there's no NASA left. There's NASA meatball under there, and probably only 2 links instead of 3 because to stay within the budget, really the ESA managers say, look, you have 3 spacecraft. Can you do it with 2? So now you cannot do interferometry with only 2 spacecraft. You need 2 arms, but you can cut in half the 2 spacecraft at the 2 ends. So in effect, you have 1 full and 2 half spacecraft, and that costs as much as 2 spacecraft. More or less, that's the reason. So the good thing is that ESA, I participated also in the science study that ESA did of this rescope mission. Maybe smaller arms may have other savings, but it's still a very compelling gravitational wave mission in space. So if next year they decide to go with that rather than with the competitors, which are a planetary mission and an X-ray mission, also missions that should have been done together with NASA, but that ESA is exploring doing alone, then that's definitely the most exciting thing that can happen. If it doesn't, NASA is going through the motions of looking at things. So if ESA goes forward, NASA will try to join as a junior partner. Definitely most of the major hardware done in Europe. But NASA can contribute something and help with the science. And I must say that the center of mass for science has been in the US. The theorists and the data analysis have been in the US with important European contributions. If it does not, NASA is studying alternative mission concepts. So it has issued what they call a request for information, and we, various combinations of people, have put in 15 alternative ideas on doing a space-based mission that try to look at different smarter ways of doing things. For instance, an exciting one is that ESA has this test masses sitting in the center of the spacecraft, and the entire spacecraft basically hovers around them. It monitors their position and pushes with microcomputer thrusters to keep centered, at least along the direction of measurement. That's a delicate thing. It's a difficult thing that needs testing. In fact, ESA Pathfinder will test it in 2014, that's a European mission. Could you do without it? Well, maybe the best way to do without it is actually what's the main source of noise on the test mass? It's actually radiation pressure from the sun and solar wind. So if you arrange for your spacecraft to be always, or for the axis of measurement to be always orthogonal to the sun, you can basically remove the effect of radiation pressure on the measurement. As for wind, you can try to measure it with particle detectors and radiometers on the spacecraft and calibrate that away. So this has not the sensitivity that the test mass has. On the other hand, you can do 20 million baselines, so 20 million kilometer baselines as opposed to 5. And you get within the ballpark of these. Still a few times worse, but enough to do a lot of the science. So this is Lagrange. It's a JPL concept led by Kurt McKenzie, who is one of our interferometry experts. The point is that still has 3 spacecraft in an Earth-like orbit in space, and just to do that, it's more than $1 billion. There's really no way around that. It's big orbits, it's several spacecraft. Takes a big rocket. It could be, a Falcon 9 SpaceX, which is very cool now and better and cheaper than Boeing, but it's still a major flagship mission that NASA doesn't seem to have the money for. So Europe is my best hope for that. So then quickly the LISA and then the new LISA or science case, a whole lot of binaries, as I was telling you. A lot of the best science comes from binaries. So binaries are supermassive black holes at the center of galaxies. They tell you about galaxies, they're black holes, they like to do cosmology, galactic binaries in our neighborhood. Extreme acceleration spirals, also very interesting because small bodies like Newton's star have better than solar mass black holes in falling into the big ones at the center of galaxies. And then always the unexpected and the exotic. So we look, for instance, for cosmological stochastic backgrounds, but we've seen that since they're most reasonable inflation scenarios, for instance, don't have a signal that's big enough for something like LISA. You could have taken the LISA successor, which used to be called the Big Bang Observer, and that the slightly different version, the Japanese are developing for the future, has decided to see that. So I'll now take these 3 things in detail and tell you about the science we can do with it. But the point of this slide was to see what you can do with a smaller interferometer. For instance, something where you don't quite have 5 million kilometers, you have 1 million kilometers, where you shrink your telescopes so you can get a little less light on the other side. And maybe you go into you go a little closer to the Earth in your orbit. So you can basically do the massive black hole mergers. These are so strong that we see them to the edge of the universe with very high contrast. Positional and distance determination is not as good, so maybe the cosmography goes out. Galactic binaries, we can certainly do them. Maybe we see half as many objects, but still several thousand binaries in the galaxy. Bursts, well, it's less sensitive, so less discovered space, but these were never guaranteed to begin with. And extreme acceleration spiral, this is yellow going on to green because it depends on the universe's generosity. So we don't see this very far. If we see this with classic LISA, we can see them to a Z01. With a new LISA and comparable concepts, we did maybe to a 0.5. So that cuts your event rate. And if the event rate was low to begin with, maybe it cuts it below 1. Okay? So, but still, if you do see them, you do very, very interesting pieces. Yeah. Okay, so the science case for black holes, I think maybe the strongest point that, in my opinion, is the coolest thing LISA can do. Because we see massive black holes all around us, nearby galaxies. Of course, we see a very famous one in our neighborhood, and we can tell it's there, we can follow orbits of stars around it very accurately. But also we see light from what can only be massive black holes from very early in the universe. And these quasars must come from very big black holes to be so luminous. In fact, we see so much light from in quasars and from active galactic nuclei early in the universe that it's a little hard to explain it with the black holes that we see today around us. It used to be the other way around. And it's clear by looking at black hole, the masses that we can infer from black holes by the motion of the stars and gas around them, and the velocity dispersions of the stars in galaxies around them. It's clear that there's a very close relation between nuclear galactic black holes and their galaxies. They have grown together. We expect through a process of hierarchical mergers, where smaller initially protohalos, then halos, and the galaxies with black holes merge successively, and the black holes at their centers also find each other and probably So several questions here that we cannot quite answer with the electromagnetic observations and the gravitational waves will tell us about. So number one, how can you have a Z06 such heavy black holes already? Where do they come from? They must come from some kind of seed black holes, which could have been the collapse of the initial population 3 of stars, heavy stars above 100 solar mass, or they might have come from the direct collapse of gas. The details of how you can do it really depend on details about the early universe and about the proto-halos, such as what metallicities you could have there. By seeing a population of tens to hundreds of black holes, and by seeing them to very early Z's, up to Z of 15 or 20, LISA or new LISA would tell us whether there are small ones as in 100 or there are small ones as in 1,000 or 10,000, what the initial ones were. Also how they grew. So they couldn't quite grow to big 10 to the 8, 10 to the 9 solar masses, which is what you see, the AGNs we see, just by mergers. You need lots of accretion. We think they grew primarily by accretion. However, accretion can come in an efficient way through a disk, which really speeds up black holes. So it can come in a chaotic way, repeated episodes from basically random animals. One of these leads to black holes spinning very, very rapidly. The other one is just spinning somewhat moderately. So spin of black holes is something you can definitely tell from these fire waveforms. So it will tell us how they grew. And finally, just the efficiency of the process. It's not easy for the black holes to merge. After a merger of galaxies, they're still actually pretty far, and to decouple gravitationally, and then to emit enough gravitational waves to actually merge, they need the help of dynamical friction from gas, from stars, and there's this last parsec problem, which is basically there may be a stalling of this process where the binary has emptied out its neighborhood of gas and black holes. There are ways to get them to merge anyway, so how many we find will tell us how efficient the process is. That's a data point that will come also from pulsar timing. Pulsar timing will look for very heavy black holes, tend to be able or so at very long periods of years by looking at the modulations of the timing residuals of pulsars observed in the galaxy. So detections of those binaries will tell us the black holes will merge. Okay. Let me move on to small binaries then. There's a lot of text here, but the point is these are compact, ultra-compact, defined as periods of less than 1 hour, binaries in our galaxy where we have a white dwarf and either another white dwarf or a helium star, which is still very compact. These actually, I like to carry them around, so the plural of white dwarf is not white dwarves, it's white dwarfs. Somebody uses white dwarf that Tolkien in Lord of the Rings. So that's something that my advisor actually corrected in the first paper that I did as a grad student. And it was in the abstract, I think. And it was really puzzled by why I would say white dwarfs as for stars. That's my classical education of time. So now we see these systems when they transfer mass. We see them as helium-rich emissions. So transfer of mass from a hydrogen-deficient container. That can only be a white dwarf or a helium star, and this is really the end point of the evolution of stellar remnants in the galaxy. They have to have gone through a common envelope phase to shed the envelope. They have to have gone through mostly one supernova, and these systems can be they shrink due to gravitational radiation, therefore the gravitational wave sources. Just because of that, but when they reach their tidal radius, they can start mass transfer. This mass transfer can be either stable, in which case they become something like AMCBMs, and actually they start evolving back to longer periods and longer by transfer angular momentum. Or mass transfer can be catastrophic, triggering possibly supernova 180 or long 180 perhaps. This is a system ground village that was detected recently. We have the details here. It's actually a very beautiful detection because this is an add-on system. So the light curve for it actually has two eclipses. Both these are one is a 0.25 helium white dwarf, 0.25 solar mass helium white dwarf. The other one is a 0.55 carbon oxygen white dwarf. You can even read off the tidal deformation on one of the two stars given by the other one from the curvature of the light curve. You can tell the mass very exactly. And also this is a pure gravitational wave emitter. There's no mass transfer here. And the P dot will be observable in gravitational waves within a year. So this is, again, check the product of the formula. But it's the other type of, so LISA or space-based will see, space-based missions will see both mass transferring and no mass transferring systems like that.
It's also computed.
Is it 13 minutes? It's, the gravitational wave frequency is 2.6 millihertz. So that would be a 1.3 megahertz. Yeah, maybe 18. So we actually, with Maya Nesaki, whom you probably know very well, and Tom Prince, and Heise Elements in the Netherlands, we've run a simulation taking some of the recent population synthesis simulations of how many of these binaries you can have in the galaxy. And we try to see what would they look like as gravitational wave sources. Now, this here was the common knowledge, the common assumption that was used to build the LISA science case and that was used in all papers for the last 10 years, let's say. It turns out that recently people have been looking for MCDS for the systems in the surveys following up SDSS, selected white dwarf sources. And they haven't quite found as many as the theoretical expectations were before. So the point to this work was to try to calibrate the population synthesis simulations with these observations and see if you still have enough out there to see them well and to study them with LISA. These are two missions actually. There was the classic one, this is kind of a smaller one. The blue is the overall, there are 100 million of these things in the galaxy, so they give you a strong signal above the LISA noise floor, instrumental noise floor. However, these dots are all the systems that you can individually take out. That's also simulated in this thing. We've actually simulated the LISA data and the extraction of signals from the LISA data. And then you take the noise down back to the spread, which is the confusion, the unresolved binary confusion for so then we calibrate the simulation, which would reduce the number of red dots, the number of mass transferring systems, by assuming that tidal coupling is not efficient, and therefore you have runaway mass transfer in a large number of systems. Results in a smaller number of ACN, but still a pretty healthy, a few hundred and 100 small LISA detections of these emission systems, for which for some of them you'll be able to measure the F dot, the double dots, so the frequency evolution, and therefore still a very, very healthy science payoff, science boundary, let's say. The green are the systems that are not mass transferring, they're evolving purely due to gravitational waves, and they actually, the number is not changed. The changes in assumptions are into the system that make it mass transfer, and those remain very, very blank. So something like this, of the 13,000 of them, even a smaller LISA sees as many as 6,000. I should also say, we know of systems like that. We know of binaries of white dwarfs and neutron stars through electromagnetic observations. We know they sit in the LISA band, and this is where would they be with respect to the noise, so very strong detections and a sampling of what we expect to see eventually. So these are known as verification sources for a space-based mission, because it will be the first thing you see. You know where they are, you know what frequency they have, and they will essentially verify that the instrument is working well. This is something that ground-based light and Virgo don't have. There's no known source that emits strongly enough to simulate, although we have strong opinions as to what their numbers and their rates. The opinions seem to change with the generation of the technology. There's a sociological limit that the lower limit on rate is 1 within the technology occurring, or maybe the upper limit. We see. So last science highlights, extreme acceleration spirals, again a small body falling into a big one. This is a very nice simulation. I think I cut off the name. This from Steve Gasko, was at GPL, the Caltech, and Gold. So they make these very beautiful orbits because they get so close to the black hole that really it's very non-Keplerian orbits. You have very strong precession of both the orbit and the inclination axis. You can go through resonances, in which case, well, it was pretty. Also, it can change the overall phase a lot. And these systems, within a year of collected data, would go through hundreds of thousands of orbits. That means they're very, for that reason, they're very, very precise probes of what the dynamics can be, because you only see them well if you can match the dynamics with an error of a few degrees within many thousands of cycles. So this kind of system answers questions about astrophysics again. It will tell us about the masses and spins of the holes, even the ones that don't merge in binaries, but just have a small thing going into them. It will tell us about the masses and spins of the small bodies in galactic nuclei that can be captured, about the process of capture, whether it comes from the equatorial plane or the galactic plane or something else. But also they tell us whether the galactic black holes are really the objects predicted by general relativity, which is the Kerr geometry. A little more about testing GR with gravitational waves. This has been the selling point for LISA in Europe, actually, for the last few years. So, general relativity is a very well-tested theory. You know, very high precision tests in the solar system, in the laboratory even. You have GPS, which needs gravitational waves. And in a way, since the 70s, there's been a standard model of what a theory of gravitation can be, which starts from the principle of equivalence, which also is tested very well, and with local Lorentz and pi. And if you put those two things together, pretty much your gravitation needs to be a metric theory. So bodies fall along geodesics. Once you do that, there's really not much you can do. You can do that's different from GR. You can add a scalar field, perhaps, which will give you other polarizations of gravitational waves, and which will change the loss of energy from the binary. You can perhaps put in a mass for the gravitational waves, although that's that's theoretically a little difficult because you don't quite get a nice action. But all these things actually are already constrained by the binary pulsar, by low energy weak field measurements in the solar system, and the few alternative theories which actually were viable were killed with the Hall-Taylor formula. So, which has a confirmation of a quadrupole formula killed off a whole bunch of theories in the 70s. I would say that it's not so much these classic tests of gravitation that will be interesting with gravitational waves. It's perhaps the sector where, okay, the test cosmology doing standard science, as I was telling you before. You look at whether the no-hair theorem applies, so whether the central objects of galaxies are really Kerr-black holes, and all the multiples, you see, mass and current multiples, are as predicted by the Kerr geometry and depend only on two parameters, mass and speed. And you can run null tests for the consistence of the general relativistic models. For instance, the post-Newtonian expansion of equations for a binary gives you the evolution of its phasing as a polynomial in the time or in the phase, if you wish. All the coefficients of the polynomials are functions of the masses and spins of the black holes. You can also treat them as independent coefficients, a bit like you do in the post-Keplerian formalism for binaries, and see whether the detection matches. I mean, if they all intersect where they should in a detection. There are also some attempts now, Eunice and Pretorius have one, to actually add artificially more coefficients there with extra powers of frequency or with extra powers of time. And you can also look for those. It's a bit of an ad hoc probe, but it does contain general relativity, so it does let you put the constraints on. Okay, how many? And the powers 20 minutes. So this was my transition slide. Because there's this phrase that's been used so much in gravitational wave science, which is the opening of the new window to the universe. So here, I raise you 6 windows. Yeah, we're really looking to see strange things and new things. At the same time, we don't really see with gravitational waves. We see this squiggles on the plot, maybe we can try to hear them. But gravitational wave astronomy won't be as direct as looking for a telescope or taking a picture. In effect, the thing that we see are the parameters of the signal. So I can tell you briefly a little bit about gravitational gravitational wave data analysis. But since I have to cut out a few slides, just apart from Kip, okay, who knows everything about it, do you know more or less the principles by which, do you know more or less the principles by which we interpret gravitational waves, get parameters? Maybe not. Okay. So then I can give you this, which is gravitational wave data analysis done with addition and subtraction. Okay, it gets simpler than that. So data is signal, the simple gravitational wave, just the sine Gaussian, plus noise. This is what you see. Your task is to go back to this, given that. Okay, so if data is signal plus noise, it follows that noise is data minus signal. Why is that important? Because we have a good idea of, given a certain noise, how probable that noise would be. So how likely is our detector to have made that noise? So for instance, we see this. Is this just noise, or is it, this noise that you get from the original signal after subtracting a certain shape, certain gravitational wave shape? If we know the noise, we can compare the probability of these two, and in this case, the ratio of the two probabilities is something like, it's the exponential something for the signal to noise ratio, is the strength, the amplitude of the signal. In this case, it would be about 300,000. So signal to noise ratio, you can more or less understand it as a sigma number. So this is as now 5, you could say it's a 5 sigma detection. And we routinely use numbers like 5 and 10, and that seem very high. It seems that the 10 sigma detection would be very high, except that you have to look for many possible different shapes of gravitational waves. And also you have to keep looking for them at all possible times. Therefore, there's a trial factor by which you're running so many experiments that you do need pretty high ratios here. The classic way to look at detection, though, is through something called match filtering or correlation, for which, therefore, I need also multiplication, okay, not just plus and minus. And which is, if you multiply a signal by itself, if there's something that's positively definite, you take the integral, it's a big number, okay? Again, as an arch level. If you multiply the signal by noise alone, you get something that's not positively definite. It actually has a noise-like characteristic. Therefore, if you integrate it out, it's going to be basically a random walk. Therefore, the number won't be as big. Therefore, if we take that data from the detector, so here multiply by a template, right, a known shape for the gravitational wave, we're going to get a number that's either bad or bad, or somewhere in between. And noise will shift it around, but there's a signal, the result will cluster around some big value. If there's not, it will not. So if you set a threshold and you say anything above that, I'm going to consider a signal, anything below, that's basically your detection scheme, your discrimination. Also science, what's science? Science is parameters, as I was saying, the determination, the knowledge that you can get about like the mass, like spins and so on. In this case, my ideal signal, I can change it around 2 axes, if this is a function of form. How do I estimate parameters? More or less the same thing. This is my original signal. I start subtracting different possible templates corresponding to different parameters. I get different realizations of noise, and the one that's actually less noisy in a way, the one that's most probable, gives it the maximum likelihood estimate for the signal, which is not going to be the exact one, the exact signal that's in there, because noise makes you make an error. But that's fine. Now, people like Carlo do numerical simulations of the final phase of binary spirals. They worry about how accurate the simulation is. So there's actually a very beautiful paper that was quite to my taste that Ilana wrote with Samaya, Misaki, and Carlo about how well you need to know to actually put together the spiral templates from Postlettonian analytic theory and numerical relativity theory. And to say this kind of thing, you have to understand what's the effect that making an error in the wave that you make has on first detection and then parameter estimation. So on detection, what happens? Say, this is really physics, this is the thing we want to see, but our model is a little wrong, so it looks like that. Well, when you take the integral, the product, correlation product, it's going to have some negative here, some destructive effect here, and therefore you don't get as much in your match filter, your correlation, and this pushes back the cluster of detection things toward the cluster of things that look like noise filters. Therefore, you lose horizon distance. You lose how far you can see, and you need stronger signals. The measure of this is the splitting factor, which is basically a measure of how much a signal looks like the real signal should be. As far as parameter estimation, it's easier to take a geometric point of view and to say that if there's a God-given or Einstein-given manifold of truth signals out there, the best we can do is approximate it. Then a signal of a certain number of parameters won't be matched. The most likely, maximum likely signal that I was showing you before won't be the exact one. I mean, won't be the signal with the very same parameters. It will have slightly different parameters. It just happens to look more like it. And therefore, you're making an error in the waveforms and an error in the parameters, which, if you're doing theory sufficiently well, should be smaller than the error that noise makes, which is proportional to 1 less than I. Because after all, it took $300 billion to build the initial LIGO, and those interferometry guys worked really hard. So it would be a pity not to use this telescope, this observatory, for its potential, because we don't have quite the right. So the measure of how well you should be is this kind of ball, this fuzzy ball of where noise is taking you around. You don't know which way the noise comes. So let me skip forward a little. These were a few slides attracted perhaps to the most computationally oriented among the group, but these were slides among the various strategies that we have to take to find the best matching template for gravitational waves. And these are the strategies that we experimented with extensively in these Monte CITA challenges, where we wanted to convince ourselves that we could really do the whole visa detection job, and that for all the different source classes. So in that exercise, we actually generated synthetic signals with unknown, with blind parameters, put them in Lisa noise, and let them out for a year time. And then various groups competed in trying to analyze those data and recover the exercise. So we experimented with many techniques. So what you're doing basically is empirical function maximization. You have to look around in a very high dimensional space of all the parameters of your system, and you have to find the best match. Not only, you have to explore around it to see what the probability distribution is for those parameters where noise will have pushed you. So many ways to do this. One that I like, especially if those is very successful, is to ask for the help of randomness, so stochastic method. And Markov-Chain Monte Carlo is the best among those, at least for the case of a physicist, because it lets you play with statistical physics. So lets you jump around in a random mode with a certain energy, which is really your giving function. And you need special tricks for that, because the space is high dimensional. You don't just want to be stepping around randomly. For instance, in some cases, we understand that the regions of maximum probability for the parameters are separated in islands. Just because of the way the signal is, you fall out of coherence by an entire cycle effectively, and then fall back in again. And in that case, you want to, among the jumps that you do in your Markov-Chain Monte Carlo in random mode, you want to some special method of island hopping. Or you can do hopping between sidebands, effectively, between 1 year cycles given by pizza motion. You want to use straight like annealing, which is where you change the temperature effectively of your energy, so that you don't quite need to find this peak. It's really hard to find this because you may jump around it randomly and not find it. If you smooth it down by raising the temperature, you have a smoother rise, and your chain has a better chance of going there. There's also genetic algorithms that I don't like very much. They're cute because you're saying I have a population, the genes are my parameters, I let them evolve, I let them mate, and the best fitting organisms survive and propagate. I think the problem with this is that you have so many rules in this game that even if you do well by the end, you're not sure why you did well, and you're not quite sure you'll do well in the future with a slightly different system. Nested sampling is something that I want to mention because it's used in cosmology, and it's actually also very pretty. There's a way to compute the evidence for probability distribution by effectively moving along contours of equal likelihood and building up to the top. And there's a very cute. This mathematics takes a little bit to understand. So let me try here. But the idea is that you can basically jump up this mountain while keeping the right factor of integration, basically to build up your reference. Just this is also used now in live in Birmingham for field implementation space. And so it's 3. So I should probably wind down, but you know, it's a tribute to Steve Jobs. The one more thing is that I have had a paper recently about what I'm convinced, and the referees were convinced, and all the experts were convinced, is effectively a new way to do something in statistical inference and parameter estimation. And what it does is the following. So for a single realization of noise, you can build a likelihood map. So you can see basically, this is again my family of signal parameters. You can say how likely are different values of the parameters, and the red dot here would be the most likely one. Now, because we don't have detections yet, we're playing this game in advance, and we're playing it to try to decide which missions. Okay, so we can't just take some data, we have to consider all possible realizations of noise. And in particular, if signals are not very strong, this shape here depends a lot on what the noise here, or what the noise actually you get. So ideally, you want to do something like that, do it many, many times with the noises, and so the shapes can be pretty different, and then take into account the variation of the shape before you can say, these are we see this 10%, 1%. However, this is a Monte Carlos.
So each PDB corresponds to a different configuration?
The same signal, just different noise that we get from the effect, because noise is noise. They're all more or less equally probable. I just did this randomly, so I drew out now noise for this is white noise.
Okay, so it's the same PSP.
Yes.
But different PSP.
Yes, yes. And they can give you, for OSNR, they can give you pretty different. So you can't really do this, because to even do one of these is a Monte Carlo, if you're going to different parameters. Then you're talking about Monte Carlo, it's an exact problem. It's 10 to the 15, 10 to the 18, 10 to the 18 flops. It's too much. So the idea is to do something a little simpler, which is just to map the distribution of these red dots. Now, if you think in Fisher matrix, it's true, there's something called the Fisher matrix, which is very simple to compute. And that gives you both things, gives you all those maps, and gives you the distribution of the red dot, but only if the signal is very strong. If the signal is so strong in particular, that the errors that you make keep you in a linear regime in the waveform. That's almost never true, unfortunately, at least for ground-based data. So instead, this is a map. This is not a likelihood map. This is a map of how often you get the red dot, the top of this, the top of the distributions, over all noise realizations. This is wiggling because I actually did numerically by taking 100,000 different realizations of the noise, and for each one running a search, finding out where the top of the mountain is, making it to decrease sometimes. So what this technique does is basically to do it analytically much more cheaply. And let me go to a simpler system to show you how that's done. So this is, they are just, your data set is just 2 points. Okay? The interferometer gives you X and Y, and your model is a circle. So the real signal is just a point on the circle. It's here, okay? Now, because there's noise, it's going to be moved around. And this is the data that you actually measure. What's the maximum likelihood point? It's the projection back to the manifold of the signals, and here's the parameter that we're looking for. So the way I was showing you how to do the histogram was basically to say, okay, I'm going to sample this, take noise points all around, for each of them project it back, and count that as a certain maximum likelihood parameter. However, you can also do transpose of that. You can say, okay, let's start with a certain maximum likelihood parameters. Which noises will get me that? All the noises in this sector. And let me now integrate the volume of this sector back so that I actually get a histogram, the probability distribution for the maximum likelihood parameter. So this is formally the integral that does that. These deltas are deltas over the solutions of the maximum likelihood equation. This is the noise distribution. This is just a volume factor. And the point is that this integral, although it looks as bad as doing the search, is actually low dimensional because you don't actually need to make all these noise realizations. you can just compute a smaller number of things, which are the projections of the noise variable on the derivatives, on the variation of the signal. So the formula is this. It doesn't look too great, but the point is that this integration here is not on the noise degrees of freedom, which can be 10,000, 100,000 millimeters. It is basically on the number of parameters squared. And it is a generalization of the Fisher formula, which is more or less contained here, with by something that contains second derivatives, and that gives you the exact map of the distribution of the maximum accuracy. Which then you can sample on Markov-Chain, you can do other things for it. You can, for instance, you can use it to see the Monte Carlo or Fraser inference. But also, this is formally the estimate of the frequentist error of the maximum estimate, so how much it moves around. It goes to Fisher, sure, the Fisher is older than it. But it's actually at least 1,000 times to 10,000 times cheaper than the Monte Carlo or Monte Carlos. So if you're interested in implementing this, talk to me. I think it can be useful, and I've been shopping it also with cosmologists, observational cosmologists, and particle physicists, which are the real frequentists, because they really have different events and different organizations. So in a way, it's published, it's looking for good applications. Okay, so that was the last test. Thank you. Questions?
How many waveforms do you need to compute the Fisher matrix?
So to make a Fisher matrix, you need all the derivatives, right? So you need the waveform and all the derivative with respect to all parameters, and then you take products, the correlations of all the derivatives against each other. For that, you go one step further and you take all the second derivatives, and you need the products of those against each other. So those are the expensive things to compute. But once you have those, the integral that I showed you is just uses those as numbers, and it's just basically a Gaussian integral that's doing something like the conversion of the volume factor in signal space and in two parameter space. So that it works because of the strong but very usual assumption that noise is Gaussian. Gaussian noise lets you partition, basically. Gaussian noise lets you rotate the bases in noise space, and this lets you take a base that's oriented along the relevant degrees of freedom for the signal. So that's how we do this dimensional reduction.
Don't have any more questions, then let's move upstairs. We have to do this. Thank you, Michele.
Thank you.